So from last time, we started looking into plasmonic waveguides. So we began this topic by asking a question like this. So if you have a metal insulator single interface, you have surface plasmon. And the dispersion relation of surface plasmon looks like this. And the question is, if you have two interfaces, very close to each other. So one way to form an interface is like having MIM, metal insulator metal structure, and the other way is insulator metal insulator structure. And last time what we've done was dealing with the second structure, IMI waveguide. Okay, and then we saw that just like in mechanical oscillators, like coupled mechanical oscillators, if you take two interfaces close to each other, the plasmons interact with each other to form a two discrete modes. Okay, so one mode is odd mode and the other is even mode. Okay, so odd mode has charge distribution, looks like this. Odd distribution along z direction, and then even mode looks like that. And then we were able to solve, rigorously solve Maxwell's equations to get IMI wave solutions. Okay, and then from that we extracted like multiple properties of even mode and odd mode. So even mode is at the same thickness. Even mode is more confined compared to odd mode, and then as A decreases, or what I mean by A is the thickness decreases, even mode becomes even more confined, and then odd mode becomes less and less confined. Okay, so and then we talked about this real material case, like we talked about the field penetration into the dielectric claddings and also the propagation distance. Okay, so these two quantities are really important because basically the field the field penetration tells you about the size of the mode. Okay, so lateral size of the mode. So if the penetration is deep, that means you have your mode size is actually pretty large. And then if the penetration is small, that means your mode is pretty well confined. And also propagation distance, of course, is important because we are talking about the waveguide. Propagation distance tells you how long the wave can propagate without too much loss. Okay, so these two quantities basically are the most important quantities in characterizing plasmonic waveguides. So the biggest difference between dielectric waveguide and metallic waveguide is that dielectric waveguide, because the guiding mechanism is total internal reflection, it is, its size, its mode size, its lateral size, which is specified as a dashed line here, is lower bounded. So it's bounded by what is called diffraction limit. So even though you make the thickness of the waveguide thinner and thinner, you cannot make your mode size infinitesimally small. Instead, your mode size actually first decreases, but after a certain point, it starts to increase. Okay, so no matter how thin your waveguide is, your actual mode size is always limited by what is called diffraction limit. Okay, so this is the most important properties of dielectric waveguide. But metallic waveguide, basically you can overcome that limit. So if you have IMI waveguide and you make your waveguide thinner and thinner, you can, as you can see here, you can make your modes smaller and smaller and way below the diffraction limit. Okay, So this is one of the biggest difference between dielectric waveguide and metallic waveguide. And of course, as we said earlier, metallic waveguide also has a disadvantage, and that disadvantage is the loss. So dielectric waveguide, the mode can propagate very, very long distance without suffering from loss, but metallic waveguide, you can only propagate like a few tens of microns, or definitely less than millimeter size. Okay, so that's one of the biggest obstacle in utilizing metallic waveguide. But at the cost of this, you can get a high confinement. So metallic waveguides are useful, not always, but in some cases when you require a extreme mode confinement. Okay, so what we are going to talk today is the opposite case, metal insulator metal waveguide. Okay, so in this case, mathematical formulation is basically the same, exactly the same. So all you need to do is to switch epsilon m with epsilon d, right? So previously, the core was metal and cladding was dielectric, but in this case, core is dielectric and metal is, I'm sorry, cladding is metal. So you can just switch the permittivity of two layers and you get the solution. So if you switch that, you get these solutions. So again, you need to satisfy this equation, can I say, the momentum conservation equation, and also these two equations, depending on the mode parity, arises from the boundary conditions, right? And then you also know how to get the solution for these equations, right? You can either get the solutions using graphical method or numerical method. There's no analytic way to solve these these equations by your hand. Anyway, similar to the IMI waveguide, you have two lowest order modes. Okay, so the lowest order mode is TM, what is called TM0 mode, and the second lowest mode is TM1 mode. The reason these are TM, the transverse magnetic, is that only the plasmons exist only for transverse magnetic polarizations. By the way, Jihan asks, could you explain why metallic waveguide has high loss? Well, that is because that is really related with how you create heat inside the material. So imagine, so let's say you have a conductivity here, okay? So conductivity times E gives you current density, right? And then the power dissipation is determined by P dot E, right? So if your conductivity is, the real part of the conductivity is large, you have a power dissipation due to the heat generation, okay? And then the metal, the conductivity tends to be large, right? And its real part is also large. So, and because of that, metals tend to create a large current if you have an electromagnetic wave inside, and that is energy loss, okay? But in dielectric, the real part of the conductivity is nearly zero, okay? Because there's no free electron, or at least very, very few free electrons. And because of that, your energy dissipation is nearly zero, and that's the reason why dielectric waveguide doesn't have that much of a loss. Okay, so that's basically the main reason. Okay, so and then as I said earlier, when I say odd mode here, odd mode means if you have a waveguide, your charge distribution is odd function. Okay, and what I mean by even mode is that charge distribution is even. Okay, and if the charge distribution is odd, let's think about the EG field. EG here is the transverse field. So because charge distribution looks like this, the EG field should look like from plus to minus, and then plus to, looks like this, right? This is the EG field. And if you draw the EG field, let's say this is the positive direction and this is negative direction, then your EG field probably looks like here and there it's positive, so it's positive. And then here it's negative, so it's negative, right? So the even function, you ended up having even function for EG if you have odd charge distribution. And similarly, if you have an even charge distribution, then your EG field should look like this, okay, opposite direction. So EG becomes anti-symmetric. And from this, you can also, and if you carefully check the other components of the electric and magnetic field, you can see that when charge distribution is odd, only EX is anti-symmetric, and all the other quantities are basically symmetric. And even mode, it's the other way around. Okay. Okay, and so let's look at, before then, there's another big difference between the MIM waveguide and IMI waveguide. So IMI waveguide, the only available solutions were these two, right? So you can call this even mode and odd mode. But MIM waveguide, the situation is different. The first two mode looks like that, but there are multiple mode if I is large. I mean, the thickness of I is large enough, because now you can support not only this and that, you can also have something like this, or even higher order modes, just like in a typical dielectric or typical PEC waveguides. If the thickness of the core becomes larger, then you can support higher order modes. Okay, so that's another big difference. Okay, so going back to Jennifer Dion's paper, let's look at the actual silver SiO2 silver waveguide. Okay, so the first case is when the dielectric thickness is large, 250 nanometers. Okay, well, 250 nanometer is not that large, but that's the largest in this analysis. If this the thickness is larger than that, it becomes more and more. I mean, there are too many modes. It's difficult to analyze. Okay, in this case, you have old mode here, and here also another old mode at the high energy, and then you have here an even mode. So two old mode branches and one even mode, and then here the black line is the decoupled surface plasma, which means you have just only a single interface. And then gray line is the MIM waveguide. with this thickness. Okay, and you can see here I color coded each point, so you can see the blue circle correspond to this field profile, and then the green circle correspond to this, and so on. And you can see here one of the one of the thing that you can immediately figure out is that look at this, A of B. I mean, if you look at this case and that case, they are both anti-symmetric mode, right? If you look at the mode profile, it's like a plus and minus here, and minus and plus there. So it's like a anti-symmetric. And here, this is also anti-symmetric, but there's a big difference. The difference is this lower case field maximum is concentrated at the interface. Okay. Instead, the uppercase here, the field maximum is not at the interface. So this is the interface. So it's not at the interface, but at the inside of the core. Okay. How come this is possible? Or if you look at this case, the symmetric case, similar things happening. In this case, you have maximum occurs at the center of the core, but here, even though the field profile is symmetric, the maximum occurs at the interface, not the core. Okay, so if you actually draw the field profile, it may look like this. So if you draw the field profile, if this is the interface, this case would look like this, right? So the maximum occurs at the interface. And then this case, it looks more like this. I don't know whether this is distinguishable enough. Okay, so that field maximum occurs at here. And some of you may realize that this is associated with the transition from the k vector inside the transverse k vector becomes from imaginary to real. Okay, so the transverse, when the transverse k vector inside the core is imaginary, that means you have either sine hyperbolic or cosine hyperbolic function, right? So you always have a exponentially decaying mode. And then once the transverse k vector inside the core becomes a real number, then now this sine hyperbolic becomes sine function and cosine hyperbolic becomes cosine function. So you have a maximum in the core rather than at the interface. Okay, and because and then if you actually calculate the dispersion relation that I showed you before, you will realize that it actually smoothly changes from the the imaginary k vector to the real k vector. And then we call this, when the k vector inside the core becomes imaginary, we call this as a plasmonic mode. Okay, because the properties of plasmon is basically you have field maximum at the interface, not in the core. Okay, so these modes we call as a plasmonic mode, and then these mode, the middle two, we call as photonic mode, because it's more like a conventional photonic guided mode. Okay, even though it's supported by MIM waveguide, the property of mode is more like a conventional guided mode. So these are called photonic mode, and the first two is called plasmonic mode. Okay, so now if you look at the case with thinner waveguide, so same material, but the core is thinner. Now you have only two modes. Okay, so the one mode you have symmetric field profile, and the other mode you have an anti-symmetric field profile, and you can see this branch here, this part is plasmonic, and this part is photonic. Okay, so you can make a distinction between the plasmonic mode and the photonic mode, and of course, plasmonic modes tends to be more confined because it inherits the property of plasmons rather than the photonic mode. And the photonic mode tends to have relatively long wavelengths. Okay. Okay, so now let's look at how the even mode and odd mode behaves as you change the thickness of the waveguide. So you change the thickness of the waveguide from 50 nanometers to 12 nanometers. Okay, and then if you do so, the even mode tends to move in this direction. Okay, and so this part is actually similar to IMI waveguide in even mode in IMI waveguide, but here in this case, if you look at this portion, when the thickness of the core is large, the dispersion relation is sometimes on the left side of the single interface MIM. I mean, single interface surface plasmons. So it's not exactly same as IMI waveguide. So when I talked about IMI waveguide, everything was pretty clear, because if you have charges here, charges there, these charges can move freely around inside the core. But in this case, it's not the case, but instead you have a dielectric core. So even though you have this type of a charge distribution, these charges cannot move in these directions, right? Charges are only moving inside the core. So that makes a bit of a complication. And so you have a kind of a non-trivial behavior. And if you go to the right figure, the odd mode is also on the right side of the single interface surface plasmons, and this is very different from the IMI case. Okay, and now let's compare the propagation distance and the penetration depth. And again, propagation distance tells you how long the mode can propagate, and penetration depth tells you about the size of the mode, the energy confinement. So if you change the thickness from 100 to 12 nanometers, the propagation length decreases significantly. And also, this depth is also decreases, which is reasonable, because you lose propagation length and at the same time you gain mode confinement. But if you actually look at the propagation length, the scale, it's too short. Okay, so it's like 50 nanometer, 30 nanometer, or 10 nanometers. So it's like the mode cannot propagate even one oscillation, and then decays away. So this even mode is not too useful for actual applications. But instead, if you look at the old mode, MIM old mode, when you change the thickness from 100 nanometers to 12 nanometers, the distance of propagation got reduced, but it's reasonable amount. You can see the distance is still a few micrometers. Few micrometer means multiple, like tens of oscillations, right? A few tens of oscillations. So it's okay to distance. And then in terms of depth, confinement, you see here penetration depth is about like a few 20 nanometers, which is decent, right? So you can basically make a confined mode with a reasonable propagation. So this can be an interesting choice for plasmonic waveguide. Okay, so now here I compare the two cases. One is IMI waveguide, and the other is MIM waveguide. I guess both of these are old modes. Okay. And if you compare the propagation length for the old mode, IMI waveguide wins. Okay, you have long propagation length, whereas MIM waveguide has relatively short propagation length. And that propagation length gets even smaller when you reduce the thickness, the core thickness. Okay. But the thing is, spatial extent, like or the mode confinement, like defined by this diagram, the IMI mode, the circles, has a minimum of like 5 micrometers, which is pretty big compared to the wavelengths. But MIM old mode, it tends to decrease as the core thickness gets reduced. Okay. So, and also, if you look at the confinement factor, so confinement factor here is defined like this. So you have core, and you have cladding here, and you have energy in both core and cladding. So if you add these two energies as a denominator, and then use the energy in the core as numerator, that becomes your confinement factor. Okay, so if you look at the MIM case, it's almost 1, right? Which means most of the energy is confined at the core. But in IMI case, here you can see that confinement factor is, 0.001, or sometimes even lower than that. That means most of the energy is actually in the cladding, which is not desirable. The mode is basically very, very dispersed, very, very wide in terms of spatial extent. So, well, this is not always the case, but like just for general, a noble metal waveguide, seems like MIM old mode is the choice for giving you the best combination of fair propagation length with extreme field confinement. Okay, but you need to make sure that this is not the absolute thing. Of course, there are other cases if you use a new materials. So graphene is one of the example. So if you take into account new materials, these conclusions can be always changed. But for a noble metal, this is the case. So people try to figure out then what kind of geometry is the best in terms of plasmonic waveguide. So again, our goal is achieving large confinement with reasonable amount of propagation. Okay, so low loss plus high confinement. That's what we want to get. Okay, and so far we looked into these two, MIM and IMI waveguides. And people also talked about these two waveguides, which is called, this is called channel plasmon polariton, and this is called wedge plasmon polariton, wedge waveguide. So channel plasmon polariton, you can see here, the mode is actually confined at the, you know, the inside the valley, okay? And then wedge waveguide, the mode is at the peak, okay? And you can easily imagine that this mode is kind of similar to MIM waveguide, and this one is kind of similar to IMI waveguide, right? It's not like entirely like IMI, but it's more like the IMI waveguide. So that's like and people demonstrated that these waveguide can also show you know, relatively good performance. And then people also figured out this what is called DLSPP. And DLSPP is dielectric loaded surface plasmon polariton. So this is nothing but you have a single interface, but in order to give you a lateral confinement, you use a high index dielectric. Okay, so the wave can propagate along this metal dielectric interface. Okay, and laterally confined in these directions. And then there's a gap plasmon polariton, which you have you know, basically two metals, and you have a small gap inside. And then the final category is the hybrid plasmon polariton. And hybrid plasmon polariton is like I'll explain later. Okay, in the next slide. Okay, so hybrid plasmon polariton is like something like this. So you have a high index medium, high index, you know, material like semiconductor high waveguide. So this is basically a waveguide, okay, dielectric waveguide. And then you have a very thin spacing, and you have a metal at the bottom, okay. So what you do, if you actually calculate the mode profile for different geometric parameters, so when the diameter of the dielectric waveguide is large, and the distance between the waveguide and the metal is large too, then the mode is almost perfectly photonic. So the mode is entirely inside the dielectric waveguide. Okay. Now, as you make the dielectric waveguide smaller and smaller, and also the thickness between these two dielectric and metal interface smaller and smaller, you can now see that the energy is actually starts to confine in the space between the metal and the waveguide, right? And then eventually, if you make these two waveguides very close to each other, then almost all the energy field is confined at this small gap. Okay, and this is called a hybrid plasmon polariton. Why this is the case? Why the field here is very, very large, even though this dielectric waveguide is not a metal, right? This is a dielectric. How come then you have a large field here? The answer is actually simple. You can think of a boundary condition. So let's say you have a very, very narrow gap in between these two. Okay, and then this one, of course, has high index. High index means well, epsilon dielectric is kind of around 10. Okay, and here free space, so epsilon dielectric is say 1. for instance. Epsilon air is 1. And then you have a metal. And then if you think about the boundary condition for the surface normal field, surface normal D field has to be continuous, right? So D1N is equal to D2N, which means epsilon 1 E1N is equal to epsilon 2 E2N. But because epsilon 2 is much, much larger than epsilon 1, E1 should be much, much larger than E2, right? So this is basically the boundary condition. Because of the large contrast in epsilon, the electric field has to be very large here compared to here, okay? And that's about the field. So if you think about the intensity, it's a square of a field. So if the index contrast, permittivity contrast is about 10, then you can achieve intensity contrast about 100 between these two modes. These two regions. So with this technique, you can achieve a very confined mode without too much loss, because field, even though some field actually leaks out to this dielectric portion, this is still almost lossless, right? So the loss is relatively small, but at the same time, you get a high concentration. So here's comparison. Here, Lm is the propagation length, and then Am is the mode size. So we want mode size to be small, propagation length to be large, right? And then this red curve is our hybrid mode, and then these green curve and the purple curve are different combinations. It's not like a hybrid mode, but it's just either plasmonic waveguide or dielectric waveguide. Okay, and if you compare these curves at the same, let's say, at the same mode size, the red curve has always longer propagation length compared to the other, right? And at the same propagation length, the red curve always have smaller mode size compared to the other, right? So basically, by doing this, people can achieve highly confined mode with reasonable loss. So this is kind of a smart combination between photonic and plasmonic waveguides. Okay, hope you guys understood what I just said. And then here is the chart summarizing different types of plasmonic waveguides. And then the important numbers here is that the propagation length and the mode size, the mode area. So we want this number to be high, this number to be small, right? And you can see here, the hybrid surface plasma, hybrid polariton is here. So you have propagation length 21 times lambda, while the mode area is 0.6% of diffraction limit. Okay, so this is very nice combination. If you compare this with simple MIM waveguide, for instance, the propagation length is shorter here, while the mode area is actually larger, which is worse, right? So I guess people is now not actively looking for, the proper combination of loss and the mode area, but still, this is an important topic in the plasmonics that making a good combination between mode area and the propagation length, and then somehow overcome this trade-off relation. Okay, so any questions so far before I move on to more application topics? Okay. Okay, so that I'll assume, sorry for that, somebody is calling me. Okay, so I'll assume that there's no question, so I'll move on. So one way to overcome this, losses is to using gain medium. So what I mean by gain medium is like oh, okay. So Jihan asks a question. What is the origin of the imaginary component of K vector, which gives rise to plasmonic propagation? This is also a very good question. And so imaginary K vector, so let me begin from here. So you have a you have a K vector here. So this K vector, if you think about it, it's related with yeah. So long story short, we can think in this way. So if you have a material with permittivity epsilon, then we say that this material has index of square root of epsilon, right? And in that material, you tend to have a K vector, which looks like a nk0. So k0 is the free space K vector, okay? So the imaginary part of K vector actually give rises from the imaginary part of permittivity. Okay, so imaginary part of the permittivity is coming from the conductivity, the real part of the conductivity. So you probably remember when I mentioned about epsilon is 1 plus I sigma omega, some like the relation between complex permittivity and conductivity. So when you have a metal, the real part of the conductivity is non-negligible. So epsilon always have an imaginary part, and because of that, epsilon becomes complex number, and because epsilon is complex number, n also becomes a complex number, and so K vector tends to have imaginary part, and the imaginary part of the K vector, of course, is interpreted as the loss, the propagation loss. Okay, and my explanation here is not entirely accurate, but it may capture the the basic reason why this is the case. Okay, so yes. So imaginary part of the K vector is related with a loss, high loss. Yes, exactly. Okay, so the gain medium. So if you have a gain media, like a quantum dot or quantum emitter here, you can by doing an optical pumping, you can overcome the loss. Okay, so you can make your waveguide without having a loss. Instead, you can even make your waveguide experiencing an optical gain, okay, by pumping the external light. And this idea is actually pretty similar to the idea of laser. Okay, so if you think about a laser actually has the similar configuration. So it's like this. You have a gain medium, and then you have a cavity, right? And then you pump the medium with external light, and then the mold is formed, and when the electron in the valence band excited to conduction band, when the population inversion happens, now you start to get a stimulated emission more than a spontaneous emission. And that's like a laser, right? And it's like laser is nothing but light amplification by stimulated emission radiation. And similar thing can happen for plasmons. So instead of having free waves here, you can also think of a plasmonic cavity. So you have metal here. And then these plasmons are going back and forth, forming a large amount of amplification, and ended up having a lasing effect. So people call this as a plasma nanolaser, or sometimes people call this as a spacer. So it's like a not light amplified, but like a surface plasmon amplification by spontaneous emission of radiation. And this can be cool because you can basically excite plasmon instead of exciting light and then couple it into plasmon. So this can be useful for on-chip light source, right? It's very, if you can do this, you can create a very compact on-chip light source that can be directly coupled to the plasmonic waveguides. And there are some experimental evidences this is possible. But the problem is, again, in order to get these conditions, population inversion condition and all these conditions, you need extremely high Q factor. High Q factor means, so the Q factor means how long a mode can oscillate before it dies out, right? So let's say Q factor, roughly speaking, Q factor of 5 means the mode can oscillate 5 times before it dies out inside the cavity. Okay, so typically to create laser, the cavity Q factor is a few thousand or a few tens of thousands, or even higher than that. But because plasmons are lossy, it's pretty difficult to obtain a high Q factor with plasmonic waves. Okay, so the Q factor, it's Q factor of a few hundred is even very challenging, and that's why a spacer is not that easy to realize. Okay, and so this thing, semiconductor, high index semiconductor, low index semiconductor, and metal type of a hybrid plasmonic waveguide has been actually suggested in order to realize the plasma nano laser. Okay, so to create highly confined light with a reasonable amount of loss, so that you can get the lasing effect. You can observe a lasing effect inside this cavity. Okay, and there are other applications like a 1D cavity, 3D cavities has been proposed. Okay, so any questions so far? Okay, okay, then I'll move on. And what else can we do with plasmonic waveguide? We can think of a compact optical modulators. So this is sometimes called plasmoster because it's like a plasmon plus a transistor. So the authors of this paper named it as a plasmoster, silicon-based modulator. And then how it works is like this. You have a basically MIM waveguide, MIM waveguide. But here the metal layer is N-type of silicon, so semiconductor, and you have a very thin layer of SiO2, so that you can by applying the voltage between these two layers, you can gate the silicon. What I mean by gating is you can change the carrier density of silicon. Okay, and now you have an input port here and output port there. And because you have an input port and output port in opposite side, you don't need to worry about the signal to noise quality, because it's the only signal you can measure is actually the output signal in this case. So the idea is simple. Here, the waveguide, you have two modes. One is this mode, this blue mode, the plasmonic mode, okay? And the other mode is this red mode, which looks like a photonic mode, okay? So you have two modes. And then when off state, which means there's no gate voltage applied, both modes are exist. And if you set the distance d to be right, then what happens is that these two modes destructively interfere with each other, so you have almost zero output. Okay, and as you increase the voltage, what happens is that you now induce charges in silicon layer. And then when silicon layer has charges, again, these free electrons can act as a loss source of loss, right? And you can see that here the red mode has more energy in silicon, while blue mode doesn't have that much of a energy in silicon. So what happens is that this induced charges basically kills the red mode, okay, and only the blue mode survives when the voltage is applied. So that when voltage is applied, you can observe a transmission, non-zero transmission. Okay, again, in this regime, there exists two modes, and two modes destructively interfere, so you get zero output. And then here you basically kill one mode, and the other mode, the plasmonic mode, only survives, so you see a non-zero output. So this is a kind of way to create a waveguide modulator. Why we do this? Because this type of a modulator is very compact. You don't need that much of a length in order to achieve a large modulation. Okay, so that's a good thing, advantage of using plasmons in light modulation. Okay, so if you look at the length of the device, length is 2.2 microns. Okay, it's very close to just 1 lambda. So it's like a pretty short length, but you can achieve. And then thickness is only like 180 nanometers. So with very compact size, you can achieve a modulation. Okay, so what else can you do? You can also do these type of things. So here you use graphene to modulate silicon waveguide. And also here also it's relatively compact. It's not that compact, it's relatively compact. So here you need about like 10 micron length in order to achieve enough modulation, but it's pretty fast. And the modulation mechanism is turning on and off the absorption of graphene. And here similarly, you can also use a gold ITO silicon structure, and you have a very confined plasmonic mode. And using this confined plasmonic mode, you can create a very compact optical modulator. And in this case, the thickness is only 3 lambda. Okay, so 3 wavelengths, and you could achieve the modulation depth of 20 dB. So it's pretty decent. Okay, so again, if I re-emphasize the reason of using plasmons in modulator is that basically you can make everything very compact. Then why compact is important? Compact means you have a small device footprint. Okay, small device footprint means small capacitance, because capacitance is about area. Okay, small capacitance means small RC time constant, which basically limits the on-off speed. Okay, so small capacitance means fast operation. And also, when you turn on and off each device, the energy that is required is also proportional to CV squared. So when C goes down, then you know, the device can be also energy efficient at the same time. So the small device footprint is very desired, and plasmons can achieve that. Okay, and then when the device footprint becomes small, then you don't need to worry too much about the loss, because it doesn't undergo too many propagations. So this is justification of why you use plasmons in optical modulators. And you can do also funny things like creating a network of MIM waveguides to do interesting functionalities. For instance, let's say if you look at this video, there is a MIM input, and then you have basically designed the waveguide junction that has exactly split the wave into 4 parts. Okay, and then if you combine these junctions in an interesting manner, what you can do is you can create what is called a programmed resonant guided wave network. So this guided network can do a color filter functionality. So if you insert a lambda 1 wave, this lambda 1 wave can only go out in port 1. But if you put a lambda 2 wave can go out to port 3 and 4, something like that. Okay, so if you actually look at the 2 by 2 waveguide, you know, you can now see the waves are, you know, gets reflected back and forth, and then actually forms a sort of a resonant feature inside this rectangle. So if you engineer these properties properly, you can get this color filter or other interesting functionalities. Okay, so people have dreamed about integrating everything on a plasmonic circuit and then combine it with existing electronic circuitry. This is like kind of grand picture of integrated plasmonic circuits. And I have final 2 slides before I finish, which is about a negative refraction. You probably remember when you actually look at the dispersion relation of surface plasmon, you have negative refraction regime. So again, if you look at this part, so this is basically your surface plasmon wavelength or surface plasmon frequency. And then if you go above that frequency, your dispersion relation gets reversed and do this, right? You saw this in previous lectures. Okay, so this is negative group velocity, right? So group velocity is because group velocity is correspond to d omega dk. Okay, so people uses this property in a smart manner, and I wrote a science paper in 2007, and this paper was like the first demonstration of negative refraction at visible frequencies. Okay, so if you look at this, the sample, the structure looks like this. You have an input port and output port, similarly in the previous structure. But what's kind of interesting is that you have a region with a different thickness of dielectric. So as you change the thickness of a dielectric, you can basically change the dispersion relation of a MIM waveguide, right? So these two plot in. So these two plot in this figure basically shows the two different thicknesses of silicon nitride. Okay, so at this frequency, interesting thing is that in this regime, narrow regime, things are become, you have basically negative group velocity. But in this thick regime, which follows the black curve, you still have a positive group velocity. Okay, so you create a structure like this. So this is your input slot, and you have an output slot there, and then you have these two regime where you have a very narrow silicon nitride. Okay, and then at low frequency, okay, at low frequency here, low frequency where both of these structure will give you positive group velocity, you have basically positive refraction, like as always. It's like you can think it as a two-dimensional prism experiment, okay? And then if you do the same measurement at this frequency, 514, where one of the thickness gives you negative refraction, negative group velocity, you now have a negative refraction. Okay, and then this is actual measurement. This is actual measurement, and you can clearly see here. It's even more clear. So this is the entrance, and then this is the surface normal direction. It reflected in negative manner, okay, and measured in this position. So this is a very clear demonstration of negative refraction at visible frequency for the first time at that time. So this can get into science and probably cited by a lot. Okay, so similar idea, but in more different geometry is given here. So now instead of having MIM waveguide, you have still MIM, but have a cylindrical waveguide. Okay, so this cylindrical waveguide, and then if you calculate its dispersion relation, here's the real part and here's the imaginary part, and you can see that you have a two modes. And one mode is positive index, and the other mode has negative index. Okay, and then you can see that here around here, the loss of blue mode becomes minimum. Okay, and if you compare the real part and imaginary part values, you can achieve 11.4. Okay, so real k divided by imaginary k. This basically roughly say how much of a propagation length can you achieve. Okay. So this value is 11.4, means this wave is not that lossy, so that you can use this for some applications. So this is a demonstration. You see the input light coming in with this wavefront, and then output light have this wavefront, right? Which is also negative refraction. So this paper uses, I mean, this is kind of an improvement of a previous demonstration using a cylindrical waveguide in visible frequencies. But anyway, the essence is the same. If you use a plasmon can provide a high confinement, not only the high confinement, but also interesting features in the dispersion relation. And the dispersion relation can be sometimes have a negative group velocity, and that negative group velocity is shown here. It has been utilized here. Okay, so this is all I prepared today. If you have any questions, please ask. Okay, so Jihyun asked, what does the blue and red curve mean in the figure? Blue and red curve means the dispersion relations of two different modes. So the blue curve corresponds to this mode, and the red curve corresponds to that mode. Okay, and this is the real part of the beta, and this is imaginary part of the beta. Beta means propagation constant. For negative refraction, is momentum conserved? This is really good question. Really good question. And the answer is yes. The momentum is conserved. But you should consider, you should discriminate two concepts. One is energy flow, and the other is phase flow, right? So in this case, energy flow and phase flow are simply opposite direction. So the way you satisfy the momentum conservation is that you have in-plane momentum here, which is same as the in-plane momentum of this guy. Okay, but the thing is, in out-of-plane momentum here is along this direction. So it's toward the interface, which doesn't make any sense, right? It doesn't look reasonable. But the thing is, phase is just a phase. I mean, you don't need to, there's no like energy conservation associated with phase thing. So energy conservation is about energy flow, right? So in this case, even though the phase looks like going backward, the energy is going forward. And that's basically the negative group velocity and positive phase velocity thing, right? Again, in-plane k vector are same for this and that case, but energy flow is still moving in this way. And then you can even sometimes think of very unintuitive cases. For instance, you have a phase flow. So free space, phase and energy are always going in the same direction. So this is phase, this is energy. And then in metamaterial, phase and energy can be in very different direction. So let's say phase is still going this way, while you can achieve energy going that way. Okay, this type of non-intuitive propagation is also possible. And you can even engineer how to play around with this. But this is really good question. And in all cases, in-plane K vector has to be conserved. Okay, any other question? All right. So, if you have any more question, you can always email me or email TAs, and we'll happy to answer your follow-up questions.